Hello, my name is Yasmin Roy, and this is my model of cellular respiration. To begin, I'd like to say please excuse my voice throughout the video, but I am sick. As you can see, we have a gigantic mitochondria with its outer membrane and inner membrane. Here on the inside is the inner membrane, is the matrix, and the inner membrane space is at the top. Everything outside of the outer membrane is in the cytoplasm, which begins the cellular respiration process. Glycolysis, the breakdown of glucose. So we begin our glycolysis wheel at the top with the 6-carbon glucose sugar. We use 2 ATPs to bring us to the next step of glycolysis, which gives us 2 pGals or G3P. From here, we go through a series of enzyme reactions, and we are given 2 pyruvates, and each pyruvate comes from 1 G3P, and each pyruvate is gives off 2 ATP and 1 NADH, which bring us at the end of glycolysis with a total of 4 ATPs and 2 NADHs. The next step of cellular respiration, which isn't an official step, is pyruvate oxidation. This occurs twice because there are 2 pyruvates. A carboxyl group is removed from each pyruvate, and it becomes the acetyl coenzyme A, the beginning of the citric acid cycle. Through the pyruvate oxidation, NAD+ turns into NADH. To begin the citric acid cycle, we start with the addition of oxaloacetic acid to the acetyl coenzyme A. The 2 carbon sugar plus the 4 carbon sugars gives us citric acid, a 6 carbon acid. Through a series of steps to get us back to the oxaloacetic acid, we first must recognize that NAD+ turns into NADH twice, and we are giving off 2 carbons from the citric acid, which brings us 2 carbon dioxides. Also, FAD is turned into FADH2, and we give off 1 ATP per turn. And there are 2 turns of the citric acid cycle because there are 2 pyruvates that turn into 2 acetyl coenzyme A's. As you can see, differing from the glycolysis, this is inside the mitochondria and not in the cytoplasm. So, from the 2 NADHs that we get from glycolysis and the 6 that we get from the full citric acid cycle, we are left with 10 NADHs. And from here, we go to the electron transport chain. Now here we can see that there are only 3 NADHs and 1 FADH2, but this is only 1/2 of the citric acid cycle. If you multiply both of these times 2, then the full citric acid cycle will be represented. Here we can see the 3 protein channels that pump the hydrogen ions through the inner membrane. The NADHs and the FADH2s carry at the top high energy molecules. These electrons are then given through the protein channels, as you can see here, and carried out, giving the energy to pump the hydrogen ions through the membrane. This energy is then given to the ATP synthase wheel. Because there is such a high gradient of hydrogen ions in the inner membrane space, they want to come back into the matrix. And this wheel, which also spins, gives the hydrogen ions somewhere to be able to come back into the matrix, while at the same time, at the bottom, this wheel, spinning in a different direction, is getting the energy to give the ADP a phosphate group that it will become ATP. For each NADH that carries a high energy electron, there are 10 ATPs that are created. For every FADH2, there are 2 ATPs created. So, from glycolysis, citric acid cycle, we are given 10 NADHs, and those times 3 is 30. From the FADH2 created in the citric acid cycle, we are given 2 ATPs. And 4 ATPs were created in glycolysis, while 2 was created in the citric acid cycle. So 4 plus 2 is 6. 6 plus 30 is 34. 36. 36 plus 2 is 38. And here we can account for the 38 ATP molecules that are created during cellular respiration.